vector with non-negative entries that add to 1 is called a probability vector. Okay, and if P is a stochastic matrix and Q is a probability vector, where PQ equals Q, Q is called steady state vector. No, that is not enough. Okay, what is a stochastic matrix? Yes, it's a square matrix where the columns are probability vectors. And if you didn't say square, I'll take it, but it really should say square. A square matrix whose columns are probability vectors. All right, so today we're going to look at Markov chains and stochastic matrices used for modeling real-world phenomenon. There's a couple of situations in here that you can use stochastic matrices and Markov chains to model, but there's actually tons and tons and tons of places where you can use this. All right, so very briefly, the reading, it said a vector with non-negative entries that add up to 1 is a probability vector. Stochastic matrix is a square matrix whose columns are probability vectors. A Markov chain is a sequence of probability vectors together with a stochastic matrix P. Oh, Warren, I put one on the table for you. So that we define a rule recursively to get from one probability vector to the next by multiplication by P. Right? So if you have to start with some state vector x0, and to get x1, you do P times x0. To get x2, you do P times x1. To get x3, you do P times x2. So you just take the previous one, multiply by P, you get the next one. Oh, yeah. This is very, very similar to the migration matrix that we did in chapter 1. Yep. Yeah. XK is also called a steady state vector. Oh, sorry, XK is also called a state vector. So any one of those is called a state vector. It's the state of the system at any moment in time. So we call it a state vector. And if P is a stochastic matrix, then a steady state vector or equilibrium vector for P is a vector Q, so that when you do apply the recursive rule and you do P times Q, you get Q back, right? So that's just going to keep happening from thereafter. Right. The steady state vector represents the limiting value of the Markov chain as k goes to infinity. So at some point, you're going to apply this recursive rule over and over and over again, and at some point, you're going to start getting the same thing back every time you apply the rule. We call that thing the steady state vector. It's a limiting value. And you're going to get that same thing regardless of where you start with initial state. And to find the steady state vector, you solve the matrix PQ equals Q. Solve it for Q. Or equivalently, you subtract Q from both sides. PQ minus Q equals 0. And then factor out a Q, and you end up with, if I'm going to pull a Q out here, I need a P, and not a 1 here, but an identity matrix, right? So that PQ minus Q equals 0. So P minus I times Q equals 0 is what you end up solving. All right, so we'll do a little demo, and I think this will be quite clear so that you can do some problems on your own. Okay, City Car one-day rental company. It has 2 locations, one on Main Street and one at the airport. Of the cars rented at the airport, 80% of them are returned to the airport. And of the cars rented on Main Street, 30% are returned to Main Street. So today, half the cars are at the airport. So we want to create a stochastic matrix that represents this situation. So I'm going to have from and to. I could have airport and downtown, airport and downtown. I should have said Main Street. Whatever, it doesn't matter. I called it Main Street. Main Street. Okay. All right. So if a car is rented at the airport, what's the probability that it's going to be returned to the airport? 80%. So I'm going to put in a 0.8 here. So if a car is rented at the airport, what's the probability it will be returned to Main Street? 0.2. And if a car is rented on Main Street, the probability it'll be returned to Main Street is 0.3. That was given, which means the probability it will be returned to the airport is 0.7. So this is really, really similar so far to the migration matrix thing that we did in chapter 1. Now we're just having cars migrate as opposed to bunnies migrate from a swamp to a garden. Yeah. Okay, so what is today's state vector? 0.5, 0.5. Yep, we have 50% at the airport, 50% Main Street. So I'm just going to label this airport Main Street here. Is that a probability vector? Yes. The numbers are non-negative and they add to 1, and any state vector is always a probability vector. It was given in the problem. Okay, so far? So if I want to know what percentage of cars will be at the airport tomorrow, I can multiply my stochastic matrix times today's state, and I'll get tomorrow's state. So 0.8, 0.7, 0.2, 0.3. Times 0.5, 0.5. And I could do the multiplication out, or I could have my calculator do it. Probably be faster to just do it out. So 0.8 times 0.5 plus 0.7 times 0.5 is 0.75. And then 0.2, this should come out to what? 0.25, so that they add to 1. Hang on, I'll look. 0.25. I'll scroll back up. So, nope, that's right. So this is, again, airport Main Street. It's always going to be airport Main Street. So what percentage of cars do we expect to be at the airport? 75%. So what percentage of cars will be at the airport the day after tomorrow? I take my stochastic matrix and I multiply by the last one, 0.75, 0.25. All right, so 0.8 times 0.75 plus 0.7 times 0.25. I get 0.775. And assuming I did that right, the next entry should be 1 minus that, because the two things should add to 1. That's airport, Main Street. Go away. Yeah. So 77.5% of the cars are expected to be at the airport the day after tomorrow. It's not necessarily half a car, because it's a percentage, right? So if there are 1,000 cars, you wouldn't have half a car. If there were 100 cars, there'd be half a car. But okay, so 3 days from now, we just do this again, right? We do 0.8, 0.7, 0.2, 0.3 times the previous state vector. See what we get. 7.225 and I get 0.7775. So this should be 0.2225. That's great, Iris. Yeah, this is approaching a limiting value, and a really strong conjecture is that that limiting value would be 77.7 repeating percent for the airport, right? And then 22.2 repeating percent for Main Street. Let's do one more just to verify that conjecture. So I'm just going to add a 7 in here and a 2 in here. Okay, so I have 0.77, 0.77775 and 0.22225. Airport, Main Street. So now I'm at 77.775% at the airport. So the pattern from these values is that we can conjecture that in the long run, the number of cars at the airport is approaching 77.7%. Okay. But we should verify this by solving for the steady state vector. Okay, and what matrix equation do you solve to get the steady state vector? Yep, PQ equals Q. Solving for Q, because Q is representing the steady state vector. P is my stochastic matrix, which in this case is, well, before I do that, first if I'm solving for something, I should have all of it on one side of the equation. So I'm going to subtract the Q. So I have PQ minus Q equals 0. Okay. And then I want to factor out a Q, right? But you got to remember that you can't commute. So I have to factor it out to the right side of the parentheses so that when I distribute it, it lands in the right place. So here I've got a P. When I distribute the Q, I have PQ minus. And then with typical algebra, before this class, we would have put a 1 there because 1 times Q is Q. But this is a matrix. So what kind of matrix times Q gives you Q? The identity. So the identity goes there. All right, so my stochastic matrix P, I know. And I just have to subtract the identity. So, oh good, I have more room because that's the matrix I have to solve. Okay, so P is 0.8, 0.7, 0.2, 0.3, right? And the identity matrix is 1, 0, 0, 1 in a 2 by 2. So if I subtract them, P minus I is negative 0.2, 0.7, 0.2, negative 0.7, right? You just subtract corresponding entries. So I have to solve this matrix, P minus I. Yep, sorry. Yeah, so I need to solve this P minus I times some unknown vector Q, which would be like Q1, Q2 would be its entries, equals 0, 0. So all you have to do is take your P minus I matrix, augment with zeros, augment with the 0 vector, row reduce, and solve. So let's do that on the calculator. Okay, so I need a 2 by 3. Oh, thank you. Yep. Yep. 0.2, negative 0.7, 0. So I've got my matrix, my P minus I, stochastic matrix minus the identity, augmented with zeros. And then I just go matrix, math, REF, matrix A. So let me just copy that. Yeah, x2 is going to be free. Yeah, so this says that, well, Q1 minus 3.5 Q2 equals 0. Q2 is free, right? So Q1 is 3.5 Q2, Q2 free. So that means there's going to be an infinite number of vectors that solve this thing, but only one of them is a probability vector. Okay. So let's just come up with one possible solution, Q1, Q2. Like if we let Q2 be, say, 2, right? Then what's Q1? 7, right? So that is one solution, but is that a probability vector? No, because the entries don't add up to 1, right? So to make a probability vector, you can just add these two together, you get 9, and you go 9ths. So that would just be like the case where I chose Q2 to be 2/9, then Q1 would be 7/9. Yeah. Yeah, like if I had let Q2 be 4, say, right? Then I would have had 4, 3.5 times 4 would be 14. And then if I added those up, I would get 28. I would get 18. So I would do 18ths in the denominator. The exact same thing as what I got when I did the 9. Find a vector that solves it, and then make it a probability vector by dividing the top and bottom by the sum of the two. Mm-hmm. Bring it back to our conjecture. 7/9 and 2/9. Does that agree with our conjecture of 77.7% repeating? Yeah, that's 7/9. Yeah. So this says that in the long run, you're going to have 77.7% of the cars at the airport, the remaining cars on Main Street, if this rule continues indefinitely.